In this lecture, we shall introduce the important proof principle of mathematical induction. Consider a unary predicate P on the set of natural numbers, and suppose that we wish to prove that the predicate holds for all natural numbers. Then we should provide an argument that P holds for each individual natural number. Now, since there are infinitely many natural numbers, it is of course infeasible to provide a separate argument for each individual natural number. And the way to deal with this situation so far has been to use the proof principle of universal quantification introduction. The principle states that in order to prove that some predicate P holds for all elements in a certain domain, it suffices to provide a generic proof parameterized by a variable ranging over the domain, showing that the predicate holds. Now, since this generic proof can be instantiated with any particular element from the domain, the conclusion that it holds for all elements in the domain is justified. Now, the difficulty with this proof method is that such a generic proof is sometimes very hard to find. And when the domain over which the quantification is the set of natural numbers, it is sometimes possible to use another proof principle that is called induction. Induction essentially makes use of the fundamental ordering on the set of natural numbers. And for induction to apply, it is also important that the predicate that we are trying to prove refers to this fundamental ordering. We shall now first discuss an example that gives you some intuition for this. To illustrate how there may be a relation between instances of a problem, we take up the challenge of making a fence of squares using matchsticks. If we have 4 matchsticks, then we can arrange them in such a way that they form a square. If we have 7 matchsticks at our disposal, then we can arrange them in such a way that they form a fence of 2 squares. If we have 16 matchsticks, then we can make a fence of 5 squares. A natural question you may now ask is, how many matchsticks are needed to make a fence of n squares, where n is an arbitrary positive natural number? To answer this question, it helps to recognize some structure in the problem of making squares with matchsticks. Let f be the mapping from positive natural numbers to positive natural numbers that associates with every positive natural number n the number of matchsticks needed to make a fence of n squares. We shall define f by considering 2 cases. First, note that 4 matchsticks are needed to make a single square. So we set f of 1 to 4. Next, let's consider ourselves in the situation that we have already made a fence of I squares for some positive natural number I. We needed f of I matchsticks to make the fence. Now we can extend it to a fence of I plus 1 squares by forming an extra square at the right-hand side of the fence by conveniently placing 3 matchsticks. So we define f of I plus 1 as f of I plus 3. Thus, we have defined a mapping f that gives the number of matchsticks needed to make a fence of n squares. The definition consists of 2 clauses. The first clause defines f of 1, and the second clause defines for all positive natural numbers I how f of I plus 1 is obtained from f of I. Note that this definition allows us to compute f of n for every n. We can first repeatedly apply the second clause of the definition until we get an expression that starts with f of 1. Since we have stepped down n minus 1 times in this calculation, when pushing f of n down to f of 1, 3 is added n minus 1 times. And then we can apply the first clause of the definition. Note that 4 plus n minus 1 times 3 equals 3n plus 1. We should emphasize here that it cannot be mathematically proved that our definition of f is correct, because it's based on physical observation. We can and shall prove later that when we accept the definition of f as valid for the process of making fences of squares with matchsticks, then we have that f of n equals 3n plus 1. This concludes our digression, which served to illustrate that sometimes when solving a problem that involves natural numbers, it is convenient to refer to the fundamental ordering on the natural numbers. We now proceed to state the principle of mathematical induction. Suppose that we need to prove that some predicate P holds for all natural numbers. Then it suffices to prove that P holds for the natural number 0, which is the first element in the fundamental ordering on the natural numbers, and to prove that for all natural numbers I, if the predicate holds for I, then it also holds for the successor of I, the natural number I plus 1. The first item is called the base case of the induction. The second item is called the step case of the induction. Let's also formulate the principle of mathematical induction as a derivation rule. To prove the universal quantification for all n in the set of natural numbers the predicate p holds, it suffices to establish p0 and the universally quantified implication expressing that for all I in the set of natural numbers, pi implies pi plus 1. If both can be established, then we may conclude that Pn holds for all natural numbers with an application of the induction rule. Let's have a closer look at the formula corresponding with the step case of the induction. Intuitively, it expresses that the predicate is passed on from each natural number I to its successor, so we shall often refer to it as the pass-on property. It should be generally proved with an application of the standard universal quantification introduction and implication introduction rules. Note that this results in the declaration of a natural number I, of which it is assumed that P holds, and then the goal is still to prove that P also holds for I plus 1. The assumption Pi, generated in the process, is generally called the induction hypothesis. It is not really essential for the principle of mathematical induction which number is taken as a starting point. We could, for instance, reformulate the principle of mathematical induction taking the integer -3 as starting point. The principle of mathematical induction would then be as follows. To prove the predicate p for all integers x greater or equal -3, it suffices to prove that the predicate holds for -3, and that for all integers I greater or equal -3, the predicate is passed on from I to its successor. We also reformulate the derivation rule for induction, letting a be some arbitrary integer, which should be fixed when the rule is applied. To prove that the predicate p holds for all integers greater or equal a, it suffices by induction to prove that the predicate holds for the integer a itself, and to prove the pass-on property for all integers I greater or equal a. We could of course also take the natural number 1 as starting point to prove that some predicate p holds for all positive natural numbers. Recall that when we considered the matchstick example, we have defined a mapping f from positive natural numbers to positive natural numbers by means of the two clauses you see over here. And then we have claimed that f of n is equal to 3n plus 1 for all positive natural numbers n. In the next lecture, we shall actually prove this claim using induction on the positive natural numbers. This concludes our introduction of the proof principle of mathematical induction.